Hello friends, myself R.D. Mahajan, Assistant Professor, MIT, Aurangabad, presenting my video on the topic Fourier Integral Representation. First example, using Fourier Integral Representation, show that integration from 0 to infinity lambda sine lambda x divided by lambda square plus a square d lambda is equals to pi by 2 into e raised to minus ax, condition x greater than or equals to 0. To obtain this Fourier integral representation, we have to perform in two parts. First part, find the Fourier transform, and second part, find inverse Fourier transform to get this integral representation. Let consider f of x is equals to pi by 2 e raised to minus ax for the condition x greater than or equals to 0, and for the condition for x greater than or equals to 0 we require to find either Fourier sine transform or cosine transform. We have to obtain either Fourier sine or Fourier cosine, and to know that we have to see the term inside the integral. Here it is containing sine term. Integral is containing sine term, therefore we find Fourier sine transform. And therefore fs lambda Fourier sine transform is given by root 2 by pi integral from 0 to infinity of f of u into sine lambda u du, and therefore it is equals to root 2 by pi integration from 0 to infinity f of u, replacing x by u in this fx, we get that term as pi by 2 e raised to minus au into sine of lambda u du, and that is equals to this is a constant term that we can write down as root 2 by pi into pi by 2 integration from 0 to infinity of e raised to minus au sine of lambda u du. Using the standard result of integration as we have used in the previous examples or the previous videos, we know that we have integration of e raised to ax sine of bx as e raised to x divided by a square plus b square multiplied by a sine bx minus b cos of bx, a standard result of integration. And to apply this, we have to compare these two results. We get x as u, a coefficient of u here as minus a, and sine of bx in this term coefficient of u as lambda. Therefore, these are the values of a and b. Use here it in the result. We get it is equals to this pi by 2 I can write down as root pi by 2 into root pi by 2. Cancel with 1. Therefore, the remaining is root of pi by 2 remains. First term is e raised to x, e raised to minus au divided by a square plus b square minus a square is a square, b square is lambda square multiplied by a sine bx minus a sine of lambda u minus b lambda cos of lambda u, bracket close, outer bracket close, and the limits from 0 to infinity. And then substituting the upper and lower limit, we have two standard values. E raised to minus infinity, we get 0, and for lower limit, it is e raised to 0 as 1, and therefore, using this, we have root pi by 2 as it is. E raised to minus infinity, it is 0. 0 to anything is we get 0. For upper limit we get 0. Minus lower limit e raised to 0, 1 divided by a square plus lambda square multiplied by sine 0, 0, cos 0, 1. Therefore, it is minus lambda. And therefore, that value is root pi by 2 minus minus it becomes plus lambda divided by a square plus lambda square. We call this as equation 1. That is the Fourier sine transform of the given function. Here the half part is over, where I have obtained the value of Fourier sine transform. Using this in inverse Fourier sine transform, we can find the Fourier integral representation. Using inverse Fourier sine transform, we get f(x) is equals to f of x is equals to root 2 by pi integration from 0 to infinity. The value of that Fourier sine transform f plus lambda into sine of lambda x d lambda. Using this formula, we get it is equals to root 2 by pi integration from 0 to infinity, the value of fs lambda from equation 1 as root of pi by 2 into lambda upon a square plus lambda square into sine lambda x d lambda. And therefore it is equals to root 2 by pi cancel with root pi by 2. Therefore we have integration from 0 to infinity lambda sine lambda x divided by lambda square plus a square or a square plus lambda square d lambda, and that is equals to f of x. Therefore we get rewriting it, this is on left hand side, taking on left hand side and transferring this to right hand side. We have integration from 0 to infinity of lambda sine lambda x divided by lambda square plus a square d lambda is equals to f of x, and that is equals to we consider the value of f of x, given f of x, as pi by 2 into e raised to minus ax for the condition x greater than or equals to 0, and this is the required Fourier integral representation. Fourier integral representation of given fx, or this is the required answer. Therefore, remember the important two parts. Whenever we require to find integral representation, first part we have to find Fourier transform, and second part we have to find inverse Fourier transform. For this particular example, in the first part I have obtained Fourier sine transform, and whatever that result we use in this inverse Fourier sine transform result to find this Fourier integral representation. One more example. Using Fourier integral representation, show that integration from 0 to infinity cos of lambda x divided by 1 plus lambda square d lambda is equals to pi by 2 into e raised to minus x for the condition x greater than or equals to 0. As the condition is x greater than or equals to 0, we require to find either Fourier sine or cosine transform. And to decide whether we are to obtain Fourier sine or Fourier cosine, we have to see the term inside the integral. Here integral contain cos term or cosine term, and therefore we have to obtain, or we have to find Fourier cosine transform. And therefore we apply the standard result fc lambda Fourier cosine transform as root of 2 by pi integration from 0 to infinity f of u cos of lambda u du. Okay, and therefore it is equals to root 2 by pi integration from 0 to infinity. This we consider as fx. Here f of x as pi by 2 into e raised to minus x for the condition x greater than or equals to 0. And therefore replacing x by u, we get that term as pi by 2 e raised to minus u into cos of lambda u du, and therefore it is equals to pi by 2 as constant, we take it outside, into root of 2 by pi integration from 0 to infinity. The remaining terms are e raised to minus u cos of lambda u du. And once again we use the standard result of integration. We know that integration of e raised to x cos of bx dx is equals to e raised to x divided by a square plus b square a cos bx plus b sine of bx. Again using the standard result of integration. And therefore comparing these two results, we get x as u, a coefficient of x in this term of e raised to x, therefore coefficient of u in this term -1, and cos of bx, coefficient of u is lambda, and therefore it is equals to this pi by 2, again root pi by 2 into root pi by 2 cancel with 1, remaining is root of pi by 2. First term is e raised to x, e raised to minus u, applying this result, divided by a square plus b square, minus 1 square is 1, b square lambda square, a cos bx, a is -1, therefore minus cos of lambda u plus lambda, b is lambda, sine of lambda u, outer bracket close, and limits from 0 to infinity. Once again, for upper limit it becomes e raised to minus infinity. We know that its value is 0. For lower limit it is e raised to 0, it is 1, and therefore it is equals to root of pi by 2, e raised to minus infinity is 0, 0 multiplied by any term we get 0, minus e raised to 0 as 1 divided by 1 plus lambda square, cos 0 is 1, therefore it is -1, sin 0 is 0, and therefore if you simplify it, it is root of pi by 2, minus minus it becomes plus, 1 upon 1 plus lambda square, and we call this as equation 1, and this is the Fourier cosine transform FC lambda. Okay, here first half part is over. Then in second part we use this result in inverse Fourier cosine transform to find this Fourier integral using inverse Fourier cosine transform. We get therefore that inverse Fourier cosine transform fx is equals to root 2 by pi integration from 0 to infinity the value of Fourier cosine transform fc lambda into cos of lambda x d lambda, and therefore it is equals to root 2 by pi integration from 0 to infinity fc lambda from equation 1. That value is root of pi by 2 1 upon 1 plus lambda square multiplied by cos of lambda x d lambda, and therefore root 2 by pi cancel with root of pi by 2. Remaining term is cos lambda x divided by 1 plus lambda square d lambda is equals to fx, and therefore interchanging the side, taking this on left and this on right, we get integration from 0 to infinity of cos of lambda x divided by 1 plus lambda square d lambda is equals to fx, and that is equals to, and that fx is given function is pi by 2 e raised to minus x, and the condition is x greater than or equals to 0, and this is the required Fourier integral representation of the given f of x. This is the required result or answer. Therefore, like first problem, here also I have performed in two parts. In first part, I have obtained Fourier cosine transform. Whatever that result, we call it as equation 1. Then using that result in inverse Fourier cosine transform result to find the required Fourier integral representation of that function. Therefore, with the help of this two simple example, I have explained how we can find either Fourier integral sine Fourier integral representation of the function for both sine as well as cosine transform. Therefore, if you are watching my videos, please like and share it, as well as subscribe to my channel for latest updates. Thank you very much.